Hi friends, in this video we are going to talk about the continuous charge distribution. So let's suppose that we have a charged plane. So there will be millions of electrons or positively charged ions present over this plane. So let's suppose it is negatively charged. So there will be millions of electrons. And what we want to do is we want to find out the electric field due to this plane at some point, let's say P. So we know when there are n number of charges, then the total electric field due to those n number of charges is given by E total bar equals to the vector sum of the electric field due to first charge plus electric field due to second charge plus so on and so forth up to plus the electric field due to nth charge. So in this way we can find out the electric field if number of charges is countable. But in this case we have millions of charges and therefore we can't sum up the electric fields due to all of them. So we need to think of something else. Okay. So what we do is we assume that the charge is continuous, that means it is smeared out over this entire surface and it is uniformly distributed. Okay. So what does it mean by it is uniformly distributed? So it means that if we divide this total surface into n number of small segments, all of them having same areas, then charge on each of those segments will be same. Okay. So we can define a quantity known as surface charge density denoted by sigma, which is total charge on the surface divided by the total surface area of the surface. So Q is suppose the total charge and S is suppose the total surface area of this surface, and therefore charge can be written as Q equals to the surface charge density sigma multiplied by the surface area of the surface. So since the charge is uniformly distributed over this surface, we can find out charge on any small segment. So let's suppose I want to find out charge on this segment and suppose it is dq. So dq will be equal to sigma multiplied by surface area of this segment. So suppose it is ds. Okay. So then we can find out the electric fields due to all of these small segments at point P, and we can sum it up to find out the net electric field due to this surface at point P. Okay. So let's suppose dE bar is the electric field due to this segment at point P. So we can write dE bar equals to 1 over 4 pi epsilon naught times dq, the charge on the segment, over r squared, where r is distance of the segment from point P, multiplied by a unit vector which points from the segment to the point P. Okay. In same way we can find out electric fields due to all of these segments and we can sum it up. So the net electric field is suppose E bar. It will be equal to the electric field due to first segment plus electric field due to second segment plus so on and so forth up to plus electric field due to nth segment. Okay. So we can write this as a summation. So I goes from 1 to n, summation of dE suffix I. Alright. And if we put formula for dE, this can be written as summation I goes from 1 to n 1 over 4 pi epsilon naught times dq over ri squared, where ri is the distance of ith segment from point P multiplied by ri cap. And in the limit of n going to infinity, that means if we divide the total surface area into very small segments, then this summation can be replaced by an integral. So the net electric field E bar becomes integral of 1 over 4 pi epsilon naught multiplied by dq over r squared times r cap. Alright. So this is the way in which we can find out the electric field due to a continuous charge distribution. Now in practice we deal with different types of bodies, so it's convenient to define these three quantities for continuous charge distribution. So if we have a long body, for example a charged wire, so for such bodies we define linear charge density. So the linear charge density lambda equals to charge on the body divided by the total length of the body. And then suppose we want to find out charge in any small segment. So let's suppose charge over this segment and length of this segment is dl, then the charge on the segment can be given by lambda times dl. Alright. Then if we have planar bodies, that means thin bodies having large surface areas, then for such bodies we define surface charge density sigma equals to the charge on the body divided by the total surface area of the body. And we saw that if we want to find out charge on any small segment of such body, then charge on this segment dq is equal to surface charge density multiplied by the surface area of the segment. Then we can encounter with this third type of charge distribution, where we have the charge embedded inside the body. Okay, so we can have a solid body like this solid cube, and the charge can be embedded within that body. So for such kind of charge distribution we define volume charge density rho. So volume charge density is given by the charge on the body divided by the total volume of the body. And then if we want to find out the charge in any small volume, so let's suppose we want to find out charge over here, the small cube having volume dV, then the charge over this cube dq is given by volume charge density rho multiplied by the volume of this selected region. So using these three quantities we can deal with almost all problems related to the continuous charge distribution. Now finally, to conclude the session, let's consider an example on continuous charge distribution. So let's suppose that we have this charged ring and we want to find out its electric field at this point P, which lies on its axis. The charge on the ring is capital Q, r is radius of the ring, and x is the distance of point P from center of the ring where we want to find out the electric field. Now first of all, we'll assume that the charge is uniformly distributed over the circumference of this ring, and therefore we can define the linear charge density for this ring. So we know that the linear charge density lambda is the charge on the object divided by length of the object. So for this ring, the length is the circumference of the ring, which is 2 pi times r. Okay. Then let's consider two small segments of this ring, one at the top and the other one at the bottom, exactly at the diametrically opposite point. Now length of both of these segments is suppose same, so dl is length of this segment and it's the same for this other segment, and therefore the charge on both of them will be equal because the charge is uniformly distributed. So charge on this one is suppose dq, and therefore charge on this one is also dq. Okay, and since the linear charge density is lambda, dq is equal to lambda times length of these elements, so lambda times dl. Okay, then we can find out the electric field due to this length element and this length element at point P. So dE1 bar is the electric field due to this segment at the top, and dE2 bar is the electric field due to this segment at the bottom of the ring. Now we can add these two electric fields due to this segment at the top and the bottom. So for that, let's resolve them along two perpendicular components. So let's suppose that this angle is theta and this one is vertically opposite angle to this one, so therefore this is also theta. And if we consider these two triangles, then we see that they are congruent because this side has length r and this side of this triangle has length r. This side is common. This angle is 90 degrees and this angle is also 90 degrees. So by SAS test, these two triangles are congruent, and therefore this angle is also theta and this one is vertically opposite angle to this one, so this is also theta. Okay, then we can resolve dE1 bar and dE2 bar. So for dE1, the component on this horizontal line will be this much, and it will be dE1 into cos of theta, and component on this vertical line will be this much, and it is dE1 into sin theta. Similarly for dE2, the component on horizontal line will be dE2 into cos theta, and the component on this vertical line will be dE2 into sin theta. And now since the charge on both of these length elements is equal and distance of point P from both of them is also equal, so let's suppose the distance is r, the electric field due to both of these length elements at point P has same magnitude. Okay, so magnitude of dE1 bar is equal to magnitude of dE2 bar, and therefore we see here that these vertical components of dE1 bar and dE2 bar, they are directed opposite to each other, so they get cancelled out. So we can cancel out dE1 sin theta and dE2 sin theta, and the net electric field due to these two will be in axial direction. Okay, so we can conclude that if we consider two length elements having same length at two diametrically opposite points of this ring, then the components of electric field due to those length elements which are perpendicular to the axis get cancelled out and components along the axis get added. So the net electric field will be along the axis of the ring. So we can say the net electric field due to ring, suppose it is E, so E is equal to integral of the axial components of electric fields due to all length elements considered over the circumference of this ring. And what is axial component? It is dE cos of theta. Okay, so dE into cos of theta. And how can we write dE? So dE is the magnitude of electric field due to one of these length elements. So dE, where dE is equal to 1 over 4 pi epsilon naught times dq over r squared. Alright, so let's substitute this dE over here, and we know that dq is equal to lambda times dl. So we have E equals to integral over the ring of 1 over 4 pi epsilon naught times dq, which is lambda times dl divided by r squared multiplied by cos of theta. So if we see in this triangle, cos of theta is this adjacent side x divided by hypotenuse, which is r. Okay, so we can write this as integral over the ring of 1 over 4 pi epsilon naught times lambda times dl over r squared multiplied by cos of theta is x divided by r. Okay, now if we integrate over the ring, only dl will change, and therefore we can take rest of the things outside of the integral. So we have 1 over 4 pi epsilon naught times lambda into x over r raised to 3 in denominator. So integral over the ring of dl. And what is dl? So dl is the small length element on the circumference of this ring. So its minimum length can be 0 and its maximum length can be the total circumference of the ring. Okay, so integrating over the ring has limits from 0 to 2 pi r. Okay, and the integral of dl is just L. So lower limit is 0, the upper limit is 2 pi r. So if we substitute the limits, the upper limit minus lower limit gives us 2 pi r. Okay, so we have 1 over 4 pi epsilon naught into lambda times x over r cube multiplied by 2 pi into r. So this is E. And then we see that lambda is the linear charge density and 2 pi r is the total length or the total circumference of the ring. So lambda times 2 pi r is equal to total charge q of the ring. Okay, so q is lambda times 2 pi r. And if we substitute that, we get E equals to 1 over 4 pi epsilon naught into q times x over r raised to 3. Okay, so this is the formula for the electric field due to a charged ring at a point on its axis at distance x from its center. And what is r here? So r is the distance of point P from the length elements. So it can be written in terms of radius of the ring and distance of point from the center of the axis as r equals to square root of this capital R squared plus x squared using the Pythagoras theorem. So we have r equals to square root of r squared plus x squared. So in terms of this, the formula can be written as E equals to 1 over 4 pi epsilon naught times qx over, we have r raised to 3 and r is equal to r squared capital R squared plus x squared raised to half, and we have third power of this, so this is R squared plus x squared raised to 3 by 2. Okay,